I really wanted to start with things. So things like computing, processing devices, and things can actually really be anything. So, it could be an electronic watch. It could be my mobile phone. It can be fridges. Fridges talk to kind of the internet, and they talk to servers, and they're all passing information around. Now, IoT was an expression actually invented by technical geeks. This may not be well known, but security people, software people, they're in their labs and they come up with acronyms. So they came up with IoT. And what it actually stands for is the insecurity of things. Now, when it got to the marketing department said, look, you can't go and you can't sell the insecurity of things. It may be extremely insecure, but we've got to call it something else. So we'll call it Internet of Things. And so in all these things, we can have all these fridges, we can have watches, we can have smart cards, we can have dolls. All these dolls are electronic, they all talk to things, they all have chips in them. And I can even have a Raspberry Pi, they're all there. And the point I need to get over to you is that most of these things are actually not very secure at all. They are, by and large, totally insecure, and particularly in the way they're interconnected. That's where I'm kind of going to. And even in my 12 minutes, I don't mind you shouting or screaming at me. Now, I can actually cover security with one slide. People write books on this, which kind of defeats me, because it's actually extremely simple. So I can take this one slide. This is a security model. Almost everything in security can be described on this one slide. And what it says is, I have things talking to things. And usually people take black boxes, so I've taken a colored one on the right and a black and white one on the left. But these are black boxes, and at the end of the day, in any system I devise, any security system, I have two boxes that have to kind of communicate with each other, and there has to be a couple of properties. So imagine, for instance, we said, okay, we want to pass some data confidentiality. From my box on the left to the box on the right, I want to be confidential. What that would mean would be that we would need to encrypt it. In order to encrypt it, we need to have a secret key. So in these boxes, we have to have properties. And we call them kind of tamper-resistant modules. And a smart card is actually a hardened chip. And a hardened chip is a sort of a tamper-resistant module. And so you say, okay, I've got these black boxes, and I need a couple of properties. I need the box to be confidential. Because if I put a secret key into this box, if you can get the secret key out, it's all kind of a bit of a waste of time. So confidentiality is a kind of a problem with the black box. I'm not going to focus on that today. That's another subject. I can still get it on my one slide. I don't need a book. But I'm going to focus on the other one, integrity. And you have these kind of moments in life. We kind of have lots of moments in life. And to many people, one of the big moments in life was public key cryptography. And it was the idea that you could actually establish a key between two black boxes. And you could actually have somebody in between watching the total communication, and they still wouldn't know what that key was. And this was Diffie-Hellman back in about 76. And that was kind of an eye-opener moment. Actually, it's almost modern cryptography comes from all this. So that was the first eye-opener. And a little later, I had another moment. And the moment happened, and in fact, it was in the days of the early smart cards and payments, and we were kind of sat around in a room, and we were trying to describe the properties we would expect the smart cards to have. And we decided that the smart card, it was, this black box thing, it's got a kind of processor and their memory and things. And we said, well, we need to have software integrity. We need the software to actually do the right thing. And we sort of had our coffee, and those days even had a glass of wine. And we said, yeah, that's it, software integrity, essential requirement. And then after lunch, we said, but how the hell do you get software integrity? How do you measure it? How do you know if the software is right? And then we get round to another little principle. First of all, we have bugs. This is the original bug The whole expression software bugs comes from it. This bug, in actual fact, was in a relay in a kind of very early computer in the States, in the Navy. And so the argument was you can have bugs of any shape or form. And the proposition I want to give to you is that we're all kind of human. If we do something, you know, we do maybe some cooking, or maybe we do some knitting, or maybe we do some programming, the probability of making a mistake is extremely high. Can any of us actually say we don't make mistakes? And I'll put it to you, we can't say that. So whatever we do in this world, software world, we are going to have bugs. We are going to do things that make that software not do what it's expected to do. And there are just two things here I want you to kind of think about. And the first one is kind of validation. So what we talk about is, are we actually building the right system? Are we doing the right thing? And that's basically a matter of validating the requirements. And then we say, good heavens, have we built the software right? In other words, that's a verification problem. And I just want to take two examples here. The one in the background was an airplane which has kind of crashed. It was a Lufthansa 2904 back in about 93. And it was landing in bad weather. And it was an Airbus A320, a little bit electronic, computers and things. And it came in on a kind of an angle, because there was kind of a bit of crosswind there. So it landed on one wheel, and it came a little bit fast for various reasons we don't need to know about. And they then tried to put on the spoilers, put the wing spoilers up, and also to have reverse thrust. And the airplane said, no, you're not going to have spoilers, you're not going to have reverse thrust. And so the pilots actually did eventually come off the runway. And that's because in the requirements, what they said was, thou shalt not have reverse thrust, thou shalt not have spoilers, unless both wheels are on the ground with 6 tons on each. Of course, because it came in on an angle, only one wheel went on the ground. And so the software said, absolutely not, you are not going to have it. Now, these are kind of pretty big programs. I want to take another one, verification one. And this is actually true, and people will still do these things. We'll have mistakes in the software of planes. We'll also have mistakes in the software of smart cards and all that goes with that. And it's the idea that in most of these kind of smart cards, you have pins. So by and large, you have some sort of authentication process to enable things to happen. And it's quite common to have a pin. I know you guys are all into biometrics, but pins still hang around a bit. And so the idea is you'd say, well, okay, it's a short pin, maybe just 4 digits. And the reason we can make it secure is we'll let you have 3 or 4 goes, and if you get it wrong 3 or 4 times, we'll just shut down. Absolutely secure, fantastic stuff. And then we get around to the programmer. So we say to the programmer, please will you program this software that if the person puts in the pin wrong 4 times, you'll shut down. That's pretty straightforward, yeah, requirements passed on. So the software guy says, yeah, absolutely all right. So what I'll do is I'll have a little counter, and every time you get it wrong, I'll count up, and when I get to 4, I'll stop. What the software programmer hadn't thought about was Mr. Hacker, Mr. Crook. Now, Mr. Crook, of course, has control of these things. He's got the card in his hand. And what he can do is he can turn the power off. He can also measure roughly what the thing is doing, because these days there are covert channels. Chips, by and large, do leak. They do tell you roughly what they're doing. So it's actually quite easy to spot in the software where he gets around to incrementing the counter. So what actually happened in the software was he basically did the test first and then incremented the faulty counter afterwards. What the hacker found was if he turned the power off before incremented the counter, he could keep on trying a pin as long as he likes. So eventually, around about 5,000, if it's a 4-digit pin, you're going to get there. So that just shows how a very simple concept in the programming can actually go wrong. So the verification, the software didn't actually do what the requirement really was, because it didn't get through. Now, at the end of the day, all these things are kind of computer devices, and they're basically all more or less the same thing. Whether it's a smart card, whether it's a Wi-Fi doll, a Raspberry Pi, what we have is we have some hardware. We then have drivers, which is the software modules that implement the hardware. We then have some operating system, and we may or may not have some sort of virtual machine like Java or something like that. And then we have the application software at the top. So what you have is you have this huge stack, as people would call it, and most of that stack is software. The very, very bottom is hardware. Hardware has failures, which people can roughly categorize. So because hardware is kind of well-known, tried and tested, you say, oh yes, I know there's so many connections on this board, there's a probability of X that in some meantime the thing will fail. You know that, you can do all that. But this software stack, everything above it, there is absolutely no way of coming up with any sensible failure rate. Because you don't actually know if the requirements were right, and you don't actually know if the software people actually implemented it correctly. And by the way, you will have had different people probably do each one of these layers. And they probably don't even talk to each other. I just wanted to ram it home to you. The big picture is Ariane 5 back in '96. About a $7 billion program. You know, there's the rockets to put little satellite things up in the sky. And they made a little software error. Somebody decided to actually try and put a floating point 32-bit digit into a 16-bit integer. And it didn't, it overflowed. And the rocket crashed. And that rocket itself was worth about $350 million. So a $7 billion program, a $350 million part, and you can get that sort of software error untracked, unspotted. Intel, remember the Pentium? Remember the floating point error? Intel's about as scientific as we can think of. Well, you would imagine they would get that right, but of course it's all code. So inside that chip, it's kind of firmware, it's code, and somebody made a mistake. So in that code, we actually ended up with a floating point error. Going back a bit, the classic one in the medical world is the Therac 25, which is a radiotherapy machine that actually went around giving radiation doses hundreds of times over what it was supposed to be because of software errors. And you take your smart card, you take your ID card, you take your payment card. Do you really believe it hasn't got software errors? It's going to have them. It's just whether you find them. Now, people always kind of say, Oriel, to raise the problem. What's the solution? Well, the truth of it is, there is not actually a simple solution. So there is no silver bullet. There really isn't. This problem is actually going to get worse because we are more and more dependent on software. And I don't care how small an object you want to give me. If it's got software in it, I can show you that conceptually it will have flaws. It's just a matter of when you find them. So the approach that you have to take is what's called defensive programming. And this is actually not well understood. You do get it in the smart card area. Smart cards have been around for an awfully long time, and security has been quite a big issue with them. But it's the idea that you have to constantly monitor your state. So what the software has to do, it has to always know where it is and whether it should be in that state. That is a totally different approach to programming. Forget all your waterfall and your agile. Defensive programming is a completely different style. And just a very 10-second frightener. If I just take a modern system, you know, I can have secure element SIM cards, I can have watches, I can have phones, I can have point-of-sale terminals, I can have Wi-Fi gateways, I can have routers, you name it. And I've got all those communication systems. You know, I got Bluetooth, NFC, Wi-Fi, Ethernet. They're all going to have problems in them. They do. So we have a system today where we're interconnecting things, and conceptually, it is totally insecure. Thank you very much indeed.
David, thanks so much for that.